Okay. Um, Greetings to everyone on this call today. I welcome you all to today's webinar on novel portable characterization and readout system for field effect transistors implemented through ESP and other technologies. Just a few housekeeping notes. Today's session is being recorded and all the participants are muted by default. You could either use the chat feature to ask your questions, or we also have a Q&A session at the end of the webinar. My name is Priya Mangannavar. I'm a micro nano electronics technical staff at CMC Microsystems. Today, I'll be providing a brief introduction to CMC Microsystems and the electronic sensor platform. The title talk for today would then be presented by Professor Ibrahim Ghafarzadeh and his team from York University. We will then take questions from the audience. So let's get started with knowing a bit about CMC. CMC Microsystems is a not-for-profit organization with a mission to lower barriers for technology adoption. In our mission, CMC delivers micro-nano innovation capabilities across Canada and, broadly speaking, deal with technologies that will enable Canada's digital economy of the future. We typically work in the domain of microelectronics, photonics, IoT, MEMS, and nanofab, and as of 2 years ago, quantum computing. We are independent of the application. It really doesn't matter what drives you, whether it's advanced manufacturing, clean tech, agriculture, or oral health sciences. We are here to provide you with the tools to carry out your research and accelerate your development. We have partners all over the world, and we are also part of many different communities. So if there's any information that you require on specific markets or you want connections in other countries, we'd be very happy to help you with that. So the infrastructure that CMC provides can be divided into three main categories. CAD, which delivers design tools, platforms, and compute infrastructure to design and develop micro and nanosystem prototypes. We deliver these capabilities either through the cloud infrastructure or on the user's desktop. We also provide fab services, which has multi-project wafer services, package and assembly, fabrication, and also travel assistance to manufacture prototypes in commercial or university-based labs. Under lab services, we provide short-term access to development platforms, test equipments, and to validate prototypes. We also provide services for products and emerging processes and products. The processes that we are talking about today, the electronic sensor platform is one such example. This platform was first demonstrated at an university lab and has now grown to become available to users across Canada and beyond. At its core, the electronic sensor platform consists of a silicon junction field effect transistor and is delivered without an upper gate. This allows for integration of a functional material, which would act as the upper gate to modulate the channel conductivity. Now, this flexibility in depositing the functional material of your choice makes it suitable for a plethora of applications. The first application for which this platform was developed was for optical or photo detection using colloidal quantum dots as the functional material. Since then, this platform has diversified into several other applications, especially in the field of biosensing. In today's webinar, we have Professor Ibrahim Ghafarzadeh and his students from Department of Electrical Engineering and Computer Science, York University, talking about how they use this platform for neutrophil detection to detect COVID-19. Professor Ibrahim has completed his PhD at Polytechnique Montreal and then obtained his postdoc at McGill University and University of California, Berkeley. He then joined as an associate professor at York University and is heading the biologically inspired sensors and actuators laboratory. I would now like to hand over the presentation to Professor Ibrahim.
Okay, hello everyone. Thank you, CMC, for organizing this webinar and for all support. And thank you all for being here. So I'm going to talk about the field effect sensing technologies, and they're using a novel portable characterization system that we have developed in our laboratory. Here is the list of the topic that are covered in this webinar. First, I will talk about the FET sensing technologies with more their advantages and their characterizations and their mechanisms. Among various sensing technology, I will more focus on open gate junction field effect transistor, and I will talk about actually I will share with you some of our research achievements that we have had using this field effect, these actually field effect transistor sensing technology. And also I will talk about some of the problem and challenges associated with characterization of this sensing technology. So to address this challenge, I will introduce a portable multi-channel field effect characterization system. So in the end, I will give you a summary of this webinar. Okay, field effect sensing technologies have attracted the attentions for a variety of life science applications. So these applications include biosensors. And so this, for examples, for the detection of the various diseases. These diseases include HIV, influenza, cancer, Alzheimer, and COVID-19. FET sensing actually devices have other applications, for example, chemical sensors. One of the chemical sensors, for example, can be pH measurement. So as you see in this, in the center of this circle, which is a field effect transistor, recognition element that can be antibody has been coated on the surface of this device for the detection of a biomarker that can be N protein associated with COVID-19. Here you can better see the mechanism of field effect transistor. The bonding between the antibody and recognition element, which is the recognition element, and the, for example, target molecule can result in the change of the charge density, and the charge density on the top of this device may result in the change of the conductivity between drain and source. Change of this conductivity will result in the change of the drain current that can be observed in the IV characterization curve. This change of the current can be used for quantification of the target molecules. So here you can see one type of the field effect transistors, which is ISFET, ion selective field effect transistor, that require a gate, a front gate. So one may argue this front gate can actually have a problem of non-uniform, for example, electrical field on the channel, specifically if we have a large number of the sensor or array of the sensors on the same chip. So from this point of view, an field effect transistor with a back gate can be a better solution. So here, actually, this is because the gate, actually, the electrical field generated by this gate can be uniformly applied on the channel. However, for higher sensitivity, we need a small distance between this gate and channel. And this may increase the macromachining actually processes, for example, such as, for example, creating these silicon oxide layers on the top of the gate and so on, and that can increase the cost of the device. So I think open gate field effect transistor, open gate junction field effect transistor is one of the very good solution as a low cost back gated with a high sensitivity field effect transistor device. So here you can see another actually type of field effect transistor. In this device, as you see, a nanomaterial or semiconducting actually nanomaterial such as PET PSS can be printed or for example, dropped in between the source and drain. So these devices are used either the back gate or front gate and have attracted the attention of researchers for many different applications. Okay, so one may raise these questions of what are the main actual reasons that these devices have attracted the attention, specifically in recent years. This is because these devices are highly sensitive, low cost. They can be actually fabricated in small sizes with a very, very low complexity readout system. So for this reason, I can say many papers have recently been published, specifically in the last 2 years, and numbers of the companies have commercialized and launched new field effect sensing devices in the market. And this is being actually continued. And now let me actually jump into the field effect transistor, OG-JFET or OG-JFET. As you know, as actually introduced this technology, this is a foundry process that has recently facilitated by CMC. This device, as you see, what is actually differentiate this field effect transistor from other devices is the backgate and also a window on the top of this device. So this window allow the direct access of the sample onto the chip, and that is the most important, most probably this is the main reason of high sensitivity of open gate JFET based on our experience. Okay, now let's share with you some of our experimental results. Here we can see a chip, an open JFET chip that we have developed through the foundry process of ESP Open JFET. This is also a zoom in of the same device. It shows 7-channel. So these 7-channel or 7 drain that can be seen in these equivalent circuits, each one can be used as an individual actually transistor, and all sources have been connected, as you see here, the single source with the back gate. So more details can be seen in our recent publication, IEEE sensors. So in order to see the functionality and the operation of the system before fabrication, we have developed console simulation, console modeling, as you see, can perfectly show the IV curves of these IV curve characteristics of these transistors. So, for example, in this curve, you can see the drain current versus the voltage drain source for different voltage gate sources. And also here you can see drain current versus the VGS for different V drain sources. So this console simulation can be used actually as a kind of the CAD tools at this stage for assessment of the functionality of the device. Okay, the next step after design, simulation, and fabrication through CMC is the test and characterization of this device. So here you can see our first effort in order to characterize the device. We use conventional measurement setup. As you see in this figure, this includes a semiconductor characterization system and open and probe station. As you see in this probe station, in this figure, indeed, this probe station enable the direct access, electrical access to the bonding pads that is needed for applying voltage and reading currents. But the instruments that can be used for applying the voltage and recording current is this semiconductor characterization system. So this measurement setup has used actually as our first try in order to characterize the system. However, this these actually setup can for these setups, using this setup for testing our chips, we had to use very small amount of the sample in order to avoid any direct contact of the sample with the other conductors or with these needles. So because there is no any, let's say, for example, the fluidic part in order to prevent the solution from reaching to other parts. So this is the challenge. We address this challenge at the first stage by developing a low complexity setup, developing a PC printed circuit board. This printed circuit board includes a spring load connectors. These spring load connectors allow the direct connection with the chip, relying on relatively large bonding pad that we can develop in OG-JFET in comparing with other technology like CMOS. So these allow us to use these spring-loaded connectors and directly connect the device with this, connect the chip with this device. So in addition to this electrical fixture or electrical setup, a microfluidic is also was also developed. As you see, this is the schematic of the microfluidics that the microfluidic was used in order to direct the sample toward the sensing side. This is important, specifically for pH sensor sensing purposes that I share with you some of our results on that. So in this setup, which is our first version of, I can say, the measurement setup, the custom-made measurement setup, include the PCB and fluidic, but still we need in this setup to use the characterization system, the standard semiconductor characterization system, as you see here. So then I can say in this device, two challenges have been addressed. One is the direct electrical access instead of using probe station, and also using this microfluidic structure that allow us to come up with a larger amount of the samples and directing toward the sensing side. And here is some of the actually experimental results that you can see. As you see, the variation again, the IV characterization curves, that again shows the current versus VDS and also current versus VGS can be seen here. Interestingly, these are very similar to what we predicted using console. And this is the main characterization curve that we need to obtain from each sensing device, each FET sensing device. And indeed, we can actually later, by increasing, let's say, for example, the samples, to measure the variation of these actually curves, either in the top figures or in the bottom figures. So we use this device for different application. Today, I want to share with you two main applications that we have already developed. We tested, characterized, and also we published the results, as I put the references for more information. Just a summary is that by changing the pH solution were directed into the microfluidic. By changing the pH value of the solution, we could see the change of the current. So the variation of the current can be seen from this figure is linearly proportional to the pH. So with this actually figure, with these results, we can claim that the OG-JFET device that can provide us a linear pH sensing, and that is one of the very important aspects of this pH measurement system. Another aspect is the repeatability. So by changing the pH from 7 to 10 and 10 to 7 in this figure, and of course can be repeated with other values, we can see the variation of the output currents. And this moves from 400, 0.400 macrovolts to 600 macrovolts repeatedly. And with this figure, we can prove that the system can repeatedly be used. And also it gives us a sense of how fast can be. For example, here we can see, for example, where the change of the current from this point to this point, it will happens in the portion of a couple seconds, and that shows that this device can very much rapidly work. So in addition to pH measurement, I want to share with you another application. Very interesting application is the DNA detections. So many papers have reported the detection of the DNA using hybridization techniques. But here with this device, we could show the presence of the DNA mass with a very small amount of the DNA on the surface of the chip in the wet and dry mode. So that is very much actually specific way of the measuring actual DNA that we have shown using OG-JFET. So as you see, again, we used the device, we collected all of those characterization curve. From those characterization curve, we measure the variation of the current, and here is the results. We can see the small amount of the DNA, the range of the 101 nanogram and maybe lower that we have recently proved, to a larger amount like 370 nanogram per microliters can linearly change the output of the sensing device. So with this actually curve that has been reported in the transaction measurement instruments, we can prove that OG-JFET can linearly measure most probably the charge of the DNAs that are charges that are created by the DNA on the surface. And this has been repeatedly tested. In each test, we have washed actually the DNA, and again, we repeated the experiments only on single chip, and without actually need of the, for example, using single time device, single time sensor. Okay, this is another actual application that I shared with you. Now let's overview a workload of OG-JFET from design to test. So the first question, if you want to design an OG-JFET, the first question that comes up is, okay, which performance you want to reach in your sensor? Which sensitivity, selectivity, maybe the power consumption, depending to the readout system that you want to use. So for achieving this, you need to come up with a specific design, actually a specification. These design specifications can be the geometry of your device, the size of the, for example, channel, the number of the channels, and other factors. So, but the second question comes up, how I can actually make sure this design actually can reach to the required or targeted performance. So we don't have any specific tools. Again, we suggest the use of the console simulation. Console can give us an idea about the functionality of the system. So the console simulation we have successfully used, and we develop a console app that in the next page will be actually introduced by one of the team members, my PhD students, Abbas Panahi, and then after the simulation, we used LEDit to design the layout and submit the design to the CMC for fabrication. After fabrication, we have two important post-fabrication steps that I will talk about that. So Abbas, if you are here, please explain this page.
Yes, I'm here. Can you hear me?
Yes.
Okay. Hello, everyone. My name is Abbas Panahi, PhD candidate at York University, Department of Electrical Engineering. Today, I'm going to talk about ESP Simulator, which is a console multiphysics app. As you can see in this picture that has been developed in console software. With this application, ESP users can access a user-friendly environment of a console app to simulate their OpenGate JFET designs and gain insights on the operation of the device and estimate the device electronic characteristics before sending the layout design for fabrication. The app has four main sections. One is parameter selection, as you can see in the picture. You can choose the main parameters for design of OpenGate JFET, which can be controlled in fabrication. The parameters such as channel lengths, doping levels, and source and drain lenses and widths, which you can include them in your design, in your layout design for fabrication, so we can estimate the effects of all of them on the sensor response. After making sure you have selected the right biasing condition and doping levels, you can initiate the computation by clicking on the compute button. Here in the second section, you can see in the picture the compute. Under compute section, you can choose the VDS, VGS biasing condition and the range of voltages, and apply them in your simulation. Depending on the size of channel, it takes time because that defines the size of sensor that you are designing. After a couple of minutes, you will get the IDS, VDS, and IDS, VGS curves at the most as the most important device electronic characteristics. Also, user can easily understand the electron and hole concentration in the channel after simulation is complete for different voltages, as you can see in the in this figure, which is the a screenshot of the app. The app also provides the access to mesh in mesh control section, where you can change the mesh structure and size for specific purposes. This was pretty much the main step you could take to simulate a design ESP simulator. I'll be available at the end of webinar for your questions. Thank you.
Thank you, Amos. Okay, so two other post-fabrication steps are packaging and test. So just actually reminding the challenges with the test of the device, we need actually to do the packaging, like whether, let's say, for example, technology like CMOS and so on, in order to do the test before actually we doing this. This packaging should actually consider both aspects of the electrophoretic and also electrophoretic aspect of the experiments that we need in any biochemical sensors. So we offer solution for both. So we provide the service for electro packaging of your chip in Biosa, and also we have developed a portable multi-channel full effect transistor characterization system that you can see in this figure. Okay, now just a comparison between the conventional method, the conventional measurement setup or conventional actual characterization method, and the proposed system. So the top figure, again, you can see the same actual figure I showed are the conventional characterization system that include semiconductor system and the probe station, and that is actually bulky and expensive, about 100,000 K for example, for $100,000 for the actually whole setup. Why the proposed system? It's low cost, easy to use, portable, and is an ideal speed electronic sensing platform for education, research, and development. So, and also in the form of the package, it is useful for fluidic electric tests that is not actually provided in the conventional method. So here is just a very brief of the fluidic fixture service that we can provide through the CMC. Indeed, this includes the custom-made PCB board for each design, and also the custom-made hydrophobic 3D printed electric and 3D printed flow layers that can be used in the package. So here is a short actual clip of how we can. So let's assume you have designed a device. Let's say, for example, OG-JFET device. Custom-made PCBs and also other layers are developed, and then we need to integrate them all together, as you see, along with the spring-loaded components with the same number of bonding pad that you have. And you can see here a fabricated device that fabricated actually package that can be used, that can be actually connected to the proposed data acquisition system or the main board. And this is the main board that we have developed. So this is the first version of our technology that include that is actually used for doing the same actually function of the semiconductor characterization system dedicated to FET. So this is why it can be provided with, it can be purchased with a very, very low cost. So here you can see the main specification of this version of our actually technology, that this is the 8-channel specification system, that again, this is the 8-channel data recording system, knowing that semiconductor characterization system has only one single channel. The range of the voltage that is covered with this device is about 10 volt. And then the maximum actually voltage can be from -10 to +10. Another thing is about the current. The maximum current is 20 milliamp that can be used for many applications, and also the accuracy of 1 macro, the microamp. We directly use actually connected to the electricity 120 AC 60 Hertz. And the measurement through this device can be performed very fast, something about 1 millisecond per point. Assuming you want to cover 10 volt voltage and you want to use the step size of, for example, 0.5 volts. So that would be 20, let's say, points, 20 points. Actually, it requires something about 20 milliseconds plus 25 milliseconds for scanning the one single actual curve. And if you have 5 VGS, that will be multiplied by that will be about 125 milliseconds. So it still is very fast. So we can provide the access to this technology through the CMC. So, okay, to support the data acquisition system that I explained, we develop also a graphical user interface. This graphical user interface has been developed by another member of the group. If Ahmed is here, he can actually explain his GUI.
Hello everyone. I'm Ahmed Roshanfar, a biosensor researcher. I developed this GUI that works on the Unix-based and Windows operating systems. It has a user-friendly UI, and based on our parameter types, it has several sections. So the users can easily set the parameters like different channels or voltages. And after the user complete these settings, the user can send these parameters with pressing on submit button. And after that, the configurations will send to the hardware, and hardware will send the related data to the GUI. Thanks for your attention, and I will be available at the end of the meeting for your proper questions.
Thank you, Ahmed. Okay, here let's have a demo. So the data acquisition system can be connected to the electricity and the USB, and then we can actually set the parameters. For example, here we selected drain 6 and the source 5, and the voltage was about 10 volt with the 0.5 volt actually step size. After connect, we just press on the submit and we see quickly the characterization actually curves. Now, in this test, we have used a sample of the DNA, and you can see with the pipette, we can easily take the sample and insert it on the top of the chip. And after that, without changing the parameter, we want to just compare the new characterization curve with actually the previous one that was done in the dry mode. And you can see here the variation of these curves. Okay, here is, so in our group, we develop actually, in addition to the console application, we develop actually 3 other parts that are, first of all, we offer the service of the packaging of your device. Here you can see 2 examples, single FET that we have recently actually developed. And the second one is the FET array that I showed actually some of experimental results today. For both, we developed these 2 packages. This is the first version of our package that can be actually, we can give the service. And the second one is this actually device, this data acquisition system that is supported with the GUI that can be used for actually research and development purposes. So this is the summary of my today's presentation. So I talk about the FETs for life science applications. I talk about the open OG-JFET specifically. That thanks to CMC for offering this to us. And I talk about the proposed services and products that are in addition to the console application, as I mentioned, CMOS custom-made packaging service, and also FET characterization system hardware and software. And we are developing has actually a new version of this device, and we provide that to the actually the network through the CMC. So let me thanks my great students that have been working actually in this. Abbas Panay, who was working actually on the OpenJFET. Most of the experimental results are from actually his work, and also console simulation. Hamid for designing the implementing the board. Ahmed for developing actually GUI, and Morteza for developing the electrofluidic fixture. And thanks for the support of the CMC, my tax answer, and your university. So thank you.
With this, I would like to thank you all for your time and wish you the best in your research and development activities. Please reach out to us if you have any questions. We are available to help you with any queries that you have. Thank you so much for joining us today. Thank you.
Thank you very much.